Okay, so we just had 2 slides left in chapter 11. It's really nothing new to us, just work and power, which, of course, we have the same formula for work we had before, where work is change in kinetic energy. But, of course, realize if it's something rotating, we have a slightly different kinetic energy formula. So also for power, of course, we still have change in work over time. Do you remember the other power formula?
Force times velocity.
Very good, force times velocity. So think about your rotational analog. Instead of force, we're using torque to cause a rotational acceleration. Instead of velocity, we would use angular velocity. So again, sort of the same thing. Good. Great. Okay, so a quick practice problem here. This one is asking for work. It says a rigid body is shown below and consists of 3 particles connected by massless rods. It's to be rotated about an axis perpendicular to its plane through point P. So it's rotating around this point P. And these are your masses. So we got M's and 2 M's on the bottom, and then distances 30 centimeters. Hypotenuse there, sort of 50 centimeters. How much work is required to take the body from rest to an angular speed of 5 radians per second? And just other question we will need there. We'll need that line. If this is 30, this is 50, what's this pink line I just drew? The height, which would be 40, if you think about a 3, 4, 5 triangle. We'll need that. Anyway, how much work is required? So what do we really need to do?
The twig. Either way, you have to have twig.
Well, you're right. There clearly is a torque, because it is accelerating. It's going from rest to 5 radians per second.
You need to find inertia.
And perhaps we need the moment of inertia, but I want, what's the formula you just wrote down 2 slides ago?
Change in K.
Yeah, essentially, we need this. We need our change in kinetic energy. We could find torque, you are right, but it won't help us in this case. If it asks us something about power, perhaps, but change in kinetic energy. So simply remembering our kinetic energy formula, it's 1/2 I omega squared, and it is changing, so it's final minus initial, but what do we know about the initial? Yeah, it starts at rest. So we really just need to figure out what all of that is. So the I part's going to be the challenge. How do we find I if we consider these to be a bunch of point masses? And point mass was one I wanted you to know the formula for moment of inertia. Except there's no half. Yeah, or mr squared was sort of our most basic original moment of inertia formula. So we just have to go through each object and do mr squared. So I'll start down here in the corner. So we've got 2m, but m is 0.4. And then what would we call r squared there? Just the distance to the rotation point in the correct units. There you go. Okay, so it's 30 centimeters away. So 0.3. And the 0.3 is squared. Okay, so that was just one object. Plus, let's do the top. So mr squared up here, m is 0.4. R, you said, was 40 centimeters, so also 0.4. But that part's squared. And our last object in the corner, well, that's really the same thing. We could have just doubled this, or we can write it all over again. I just need one last thing to add on to this. All of this in the parentheses was just finding the moment of inertia of this system. I've got my half. What's my last missing part? Yeah, which is in the units I want. So I just need to put a 5 squared on the end there. So take a second, see if we can get some similar answers. Okay, good. 2.6, and this is work or energy. What was our unit there? One letter? Good, joules. There you go. Okay. So that's kind of the end of chapter 11. Chapter 12. What's going to be different? This is sort of a nice, it's nice that it relates all the rotational equations we just learned to all the linear ones we already knew, which we've been talking about the whole way, how they're similar. So again, if you understand how the variables relate, hopefully you only need to know one set and you will know the other set.